Hi everybody. All right, another online class. This is not expected. I thought we'd be back in person again. Of course, last week was a recorded lecture, and so I thought this week would be live, but the weather did not cooperate. So let's take a look at a couple of announcements before we get into the lecture. First of all, homework 1, which is covering some material from Chapter 7, that is due today, Tuesday. That should be uploaded by 3:30 p.m., which is the time of our class. The next assignment, homework 2, which is related to Chapter 8, some of the questions that are shown there, that's due next Tuesday. So that should be uploaded by 3:30 p.m. next Tuesday. Now, also next week, on Thursday, is the Winter Technical Conference, and I know that many of you are going to be involved with that and hopefully attending the sessions, and I don't want to cause any interference between the conference and class, so that day's lecture is going to be posted online as well. All right, today's material is covering pipe friction, sizing, and some design-related issues. It's sections 1 and 2 in Chapter 8 of your textbook. There are a couple of examples that I'll be working through in this lecture, and as previously, this is a class from a different semester, and so I'm going to be editing out their announcements, and I think for the most part the rest of the material should be the same, but if there are any casual mentions to other dates and times, then of course it's these announcements that are governing our course. Also, if you have any questions, please feel free to stop by during my office hours. I plan to be here in spite of the snow, or of course you can send me an email, and if you got any questions, just let me know.
All right, so we've seen the Moody diagram before, and the idea here is that if you know the material type of the pipe, then you have the equivalent sand roughness, K sub S. If you know the diameter of the pipe, then you can calculate the relative roughness, which tells you which of these curves you're going to be following. And then you're looking for an intercept with the Reynolds number for the flow conditions in question. And then following the intercept over to the left, that gives you the friction factor. But the question comes up, like, where did these curves come from? What are they based on? And maybe more importantly, is there any numerical way that we can calculate F without having to go to this figure? Because later on, both in Excel and in design software, we don't want to have to be stopping every time a pipe is doing a calculation to manually follow a curve on a page. And so there are, in fact, equations, and the Colebrook equation is what this set of curves is based on. Now here's the Colebrook equation. It's valid over a wide range of Reynolds numbers. Basically, the Colebrook equation you can use for anything where the Reynolds number is above 2,000. If it's less than 2,000, there's this strange little curve here in the laminar range. You can estimate F just by having 64 divided by the Reynolds number. But, I mean, that's maybe a point of trivia more than anything that's actually useful, because it's so uncommon that we would have flow conditions with a Reynolds number that low. So in all other cases, the Colebrook equation is valid. What you'll notice about this equation is it uses the K sub S to D, and so the equivalent roughness is one of the factors that goes in there. K sub S here, in your book, the symbol that's used is epsilon. But K sub S is more commonly used to mean the equivalent sand roughness, and so it's related to the material of the pipe. So that's one part of what determines it. Now the second term includes Reynolds number, but then you'll notice the friction factor F is on both sides of the equation. Hi, Jason.
Sorry.
The F being on both sides of the equation, that makes it what's called an implicit equation. And implicit equations are tricky because what you're solving for is on both sides of the equation. And what complicates things even further is it's not in a nice, easy place. It's buried in a square root in the denominator of something that you're adding a term to, and it's in a log. So you can't algebraically rearrange this and magically get the F value on only one side of the equation. The F value is going to stay on both sides of the equation. So the way that you solve an implicit equation like this is either with a good calculator, and by good calculator I mean a non-Casio. I think the Casios can solve this, bless their little hearts, after a few minutes of spinning their wheels, but the more convenient way of doing it is with the is with an equation writer on a real calculator or with Excel. And so we're going to do an Excel demonstration today. And so here's a table of K sub S values, and your book has one similar to this for a variety of different material types. But really, the tricky thing is that the F value is on both sides of the equation. So let's just use as an illustration that we have a pipe diameter of 136 millimeters. It's galvanized iron, and galvanized iron gives us this equivalent sand roughness. And we have a flow of 200 liters per second going through the pipe. So we want to find the friction factor that we're going to use. Now Reynolds number is going to make use of that flow rate. We're going to need the diameter, both in the Reynolds number and here. Let's see how we would tackle things if we just started off like trying to do the iteration on paper. First of all, we would use the diameter of 0.136 meters, K sub S of 0.15 meters, I'm sorry, 0.15 millimeters. The area, pi d squared divided by 4. And this turns into 136 millimeters. I'm expressing in terms of millimeters because when we have the equivalent sand roughness in millimeters, we'll want the ratio of the two to be in the same units. And finally, we're given a flow rate here is 200 liters per second, which is 0.20 cubic meters per second. All right, so we can find the velocity by Q divided by A. We just calculated the area, so 0.20 cubic meters per second divided by our area, 0.01453 meters squared. That's 13.77 meters per second. And so the Reynolds number then is going to be the velocity times the diameter divided by the kinematic viscosity. Okay, so the velocity, 13.77 meters per second. The diameter, 0.136 meters. And the kinematic viscosity of water, typical value, as it says on the screen there, is 1 times 10 to the minus 6th meters squared per second. So 1 times 10 to the minus 6th meters squared per second. All right, so the Reynolds number for this is 1.8 million. To be precise, 1,872,413. So that's our Reynolds number. Now, what we're going to be doing is substituting all of this information into both sides of the Colebrook equation. What we could do is we could have, let's just say, a series of iterations where we guess an F value and then we see what's the left-hand side of the equation, what's the right-hand side of the equation. So for instance, if I had F is 0.02 as my first guess, is that the right F value? I'd substitute that into the left-hand side of the equation. So I would put that guess of 0.02 down here in the denominator under that square root. And the left-hand side would turn out to be 7.071. And follow a similar approach on the right-hand side. So 2.51 divided by this Reynolds number that I calculated, multiplied by the square root of the guess F value, and I'd get the right-hand side is 7.024. So that's pretty close, but they're not equal yet. And we haven't converged on the correct F value until the right-hand side equals the left-hand side of the equation. And so I could repeat that process with an F of 0.01. That's going to give me a left-hand side of 10, a right-hand side of 7.013. So it looks like I went in the wrong direction. But actually going from 0.02 to 0.01 made the difference bigger rather than making the difference smaller. So maybe I should try a bigger F value. Now this is really inconvenient to do with a calculator by hand, but it's simpler to do when we use Excel. So if you'd like to follow along, I'm just going to start up Excel and try the same thing, a trial and error approach of solving the Colebrook equation. I'm going to dim the lights for this one just in case it's easier to see the small type as we go through. All right. For simplicity's sake, I'm going to paste the formula from the PowerPoint into the Excel file just so we've got it as a reference there. All right. So from the initial given information and the calculations I did before, we had the K sub s in millimeters was 0.15. We had a diameter of the pipe in millimeters, that is 136 from what was given previously. And then the Reynolds number that we calculated on the whiteboard was 1.87 times 10 to the 6th. All right. Now, I'm going to have a guess value of f, and then I'm going to have it calculate the left-hand side of this equation based on that guessed f, the right-hand side, and then I'm going to actually calculate the difference just so that I can know when I've converged all the way. You want it zoomed in? All right. There we go. Yeah. Thank you. All right. The range of f values, like the smallest typical f value you'd ever see is about 0.008. And the largest f value you'd ever see is about 0.038. So I'm going to, just as a first check of things, let's do it in increments of 1/1000th until we get to 0.038. All right. So the left-hand side, we're just going to say equals 1 divided by the square root of whatever this guess f value is. And we get the left-hand side of the equation. That's not what I wanted to do. There we go. That's better. All right. Now the right-hand side is going to be a little more tricky because that's the complex side of the Colebrook equation. Okay, so equals -2 times the log. And now we have to put in a K sub s. I'm going to anchor that because we're going to drag this down. We always want it to refer to that same cell location. Divided by 3.7 times the d value, also anchoring the diameter reference. It's F4. And it'll put those $ in front of both the letter and the number. And if you push it again, it'll cycle through, alternating between if it's only in front of the letter, only in front of the number, and so on. Okay, so I've got the first term. Now I need to add the second term. 2.51 divided by the Reynolds number times the square root of f, which is this. I probably have some unnecessary parentheses in there. I wish there was some way to make the formula up top a little bit bigger than it is. Anybody know of a good trick for that? I don't. That makes the formula box bigger, but I don't think that makes the text any larger, does it? Just the formula. All right, so we're not there yet. Let's find the difference. Oh, this is doesn't need to be scientific notation. Okay, so the difference is going to be 1 minus the other. Actually, I think I've got an error in my formula now that I... 7.01? Oh, no, it's fine. All right. Now, 7.01 is what it should be. Now, when in doubt, throw it out. Don't try and find the mistake in your formula. It's easier just to type it in fresh. So let me type it in fresh, and I'm going to show you kind of like a shortcut that I sometimes use to eliminate how many parentheses you have to put into a formula. Okay, so I'm going to type this in again. -2 times log. The first number is going to be the k sub s. K sub s divided by 3.7 divided by d. I need to anchor those references. So you divide by twice, and so you don't have to put in the parentheses. You know, like it executes the divided by 3.7, finds the number, and then you're dividing by the d. And so it's the same thing. So it eliminated a couple of parentheses there. Plus the right-hand side, 2.51 divided by the Reynolds number, anchoring that, divided by the square root of f. If that's the first time you're thinking of it that way, it seems pretty weird, but it'll become natural. Oh, I need to put in a multiply here. Actually, I guess I don't need that parentheses. All right. 7.01. Same thing as before. So now the difference is just one minus the other, and that there is any difference tells us that we haven't converged. Now, of course, once you've got the formulas typed in, then you can have it apply that for all of them, and we find the crossover here is somewhere in the range of 0.02, which was that first calculation we did on the board. It's more than 0.02, but less than 0.021. And of course, students of Excel know that you can do the goal seek. So it's here data, what if analysis, goal seek, and our objective here is to make the difference equal to 0 by changing the guess value of f. So it will iterate that guess value of f many times until it finds the 0 difference. And so now we've converged on the correct f value according to the Colebrook equation. Yeah, technology. All right. Now I apologize for the late notice on the laptops. The basic rule of thumb is we're going to use Excel most of the time. So, I mean, if you bring your laptop in every class period, you'll have probably some opportunity to use it. Yes? Yeah, that's right. You don't have to have a table of all of this range of values. Right. Sure, I'll show you that. So let's say that our original one was 0.008. It's here under, normally you are in home. So you'd go to data, and then what if analysis, goal seek. And our goal is we want the difference between the left-hand side and the right-hand side. That difference should be 0. So I tell it set cell D7 to value, and you have to have a numerical value for the goal. You don't in Solver, but here in Goal Seek you do. So we'll just put value 0 by changing our input guess value of f. And let it do its thing, and it finds the value. So that's an implicit equation. Colebrook equation is the most accurate, and it's always applicable. The Jain equation is pretty good. It's a little less accurate, and it's usually applicable. If we look at the range of values over which it's applicable for a range of k sub s to d values, and over most Reynolds numbers, from 5,000 until 10 to the 8th. Now, the Jain equation is an explicit equation. And that doesn't mean it's like dirty or anything. It just means that it calculates the value directly. All right, so we don't have the f value on both sides of the formula here. It's just on the left-hand side. And so we have everything we need on the board already to calculate the f value according to the Jain equation. So let's try that. From the previous example, let's see how the Jain equation does at estimating, and that will give us an idea of how accurate it is compared to Colebrook. You know, what are we giving up for that computational simplicity? So I'd like you to try that out. Calculate the F value based on the Jain equation. So when we make the substitutions, you'll actually find that it's the same F value that we got when we were doing the Colebrook equation. That F value is 0.0203. And so why is it so good in this case? It's because we're right in the middle of the range for which the Jain equation is applicable. And so you usually get pretty good results. And during the semester, it will be fine to use Jain unless you have some specific instructions to use Colebrook instead. And so if it's a homework problem or a quiz or an exam where I'm just wanting to test whether or not you understand and can apply Colebrook equation, then you should do Colebrook. But otherwise, I don't want to waste too much of your time, and the Jain equation will be just fine for you to use. Yeah? So like as a starting point? Mm-hmm. Yeah. Yeah. There, and that idea of trying to have a good guess, we do that a lot, especially later on in the semester. We look for shortcuts instead of starting with the bad guess, because there is, I don't know what's going on out there. Somebody's just fascinated with the opening and the closing. Some guy wearing like a hard hat or something. Now they're going to start on our door. He's going up and down the hall. He just can't get enough of it. Safety? Maybe. They're doing the finger pinchy experiment today. Yeah.
So if we have to do Colebrook on a quiz or an exam, then our calculators can't do it? So
No, your calculator can do it. It can. It takes a minute. Yeah, in fact,
can you show us how?
no, I can't show you how. No. But honestly, I think that I've got a recording of Dr. Pearson. Any of you ever have Dr. Pearson? So I think he used the emulator. So it'll go a lot quicker than yours will. I think the emulator's quicker, but you won't be asked to solve the Colebrook equation on the FE. I think I can tell you that much. Yes?
So the diameter of the pipe in the case of S, those have to be, you manipulate them to be the same.
Yeah, very good. Yeah, and you bring up a good point. I was going to tell you about the two most common mistakes when people use the Jain equation. One of the most common mistakes is that they would leave diameter in meters, but K sub S in millimeters, and then you're in bad trouble because it should be unitless. All right, I can't, I got to find out what's happening out here. See, it's like a watched pot will never boil. I don't know. Since I'm being recorded, I'll probably watch my language, but... All right. The second most common mistake is... people forgetting the squared. So it's easy to overlook. Don't forget to square the denominator, especially because, you know, with the logarithm, it makes you think maybe you're done, but you're not. You got to square that.
It was just a couple of people who went in next door.
Is it the next door door? I think I know who. Yeah. Hi. Hey, when you guys come in here, could you door? Because we already started next door and it's very noisy. Thanks. I'm not sure how many of them understood me. The Blasius equation is only valid for a Reynolds number up to 100,000. And it's another one of these really easy ways to calculate the F value. And just to get a feel for that, if we applied the Blasius equation to the situation we just did, where we had a Reynolds number of 1.87 times 10 to the 6th. So let's give that a shot just to see how the Blasius equation does. You know, it's good under the right circumstances, which is up to 100,000. But what you can see is I think the people who needed the announcement are still coming in late, right? Maybe I'll come and remind them again at the end. So 0.316, and the Reynolds number is 1.87 times 10 to the 6th. And we do that to the 0.25 power. All right, then we get an F value there of, according to this, 0.008, right? 0.00854. Okay, so we're well outside of the range that it applies, and the Blasius is never going to be as good as the Jain or the Colebrook equation. So, I mean, I mention it just because there are some circumstances where it can apply, and there are some references that mention it. So you need to be aware of it and what it's all about. But here, we're outside of the useful range. Okay, so sometimes we need to size pipes based on a known head loss. And a known head loss situation could be that we are starting at an elevated water storage tank, and that's what's pressurizing a pipe network, is some big Z1. So let's say here is our ground level, and we've got a big water tank. Here's the water level. Here's location 1. It's pressurizing the pipes underground. So we have the water coming out here, and it's filling a bucket or something. So the location 2 is here, where you've got an open orifice in the network, and the difference in energy is all going to be as your head loss. So this is an expected head loss. The H sub F is all of the energy that was at 1 is going to be expended over the transit to location 2. All of it's going to be expended as friction loss. There will be a little bit of energy in the velocity head. But you remember at the end of fluid mechanics last semester, we looked at how much energy is there really in velocity head, and it's not much, because velocity head, v squared divided by 2g, ordinarily the water is going to be flowing at less than 1 meter per second through the pipe. And so there's just really not very much energy tied up in velocity head. If you think about 1 squared is going to be 1 divided by 2g, so that's going to be divided by 19.62.
This is relevant, but when you have a pipe that's underground, can you have pressure added to the depth underground?
Pressure added to the depth?
Yeah, like to the water from it being underground at a certain depth.
Well, here the water, there's more water pressure in the pipeline here than there is when you go back up above the surface. And also, if you had a hill, let's say that the hillside is sloping this way, you're gaining pressure because you're getting further and further away from there. But there's not like anything magical, just like the soil pressure on the pipe. That's not going to get any usable pressure that way. Okay, so here the equation that's shown on the screen here is just the energy equation. rearranged to solve for h sub f, and we're leaving off the velocity heads. The velocity heads there, v1 squared divided by 2g and v2 squared divided by 2g. We've eliminated those just because there's very little energy in the velocity head. So sometimes you know the h sub f, and you know how much water is going to be consumed in a certain area by looking at the population in a location, the per capita water uses, maybe it's an industrial use, and you just have from the company that's going into a location an idea of how much water they require. So the Q is going to be specified, and what we're having to match is the pipe size that gives you that much head loss under a certain flow rate condition. On our first class day, I gave you sort of a sneak peek of the project that we're going to do this semester, and that's like a network sizing. And the pipe network sizing is always juggling how much pressure you've got at a certain location versus the pipe size. And if you make the pipe size smaller, then you're going to be reducing how much pressure there is at a location. And so here, this idea of finding the required diameter is going to be matching ever smaller pipe diameters until you have the head loss that matches those flow conditions. So the difference between design and analysis is in design you're optimizing and you're iterating over and over again until you have the ideal pipe diameter that gives you exactly the amount of head loss you can tolerate. So there is a conversion that we can do to find out when you have a known h sub f, the formula that you use for calculating the d from that. And I just want to show you a couple of the steps that we went through in order to get that formula that's on the screen there. It's on a subsequent slide as well if you've already printed those out. Well, let's just say that we have this, the Darcy-Weisbach equation for h sub f. Okay, that's FLV squared divided by D2G. Now we already know that V is Q divided by A. Now for that situation then we can substitute V squared. We're going to, instead of writing V squared, we're going to have Q squared divided by A squared. And the reason for that is we don't know what diameter the pipe's going to be, and so we don't know the velocity of the water flow. But we can express this in terms of the flow rate, Q, that's a known, and the area we can express in terms of D, the diameter. And so just to make you aware, we make that substitution so that now we have FLQ squared divided by D2GA squared. All right. And we'll substitute in the formula for pipe area. So it's FLQ squared D2G. And now here's our area, pi D squared divided by 4. And we're squaring that whole area. And now, since we have that 4 that's getting squared, we can rearrange and also move that up to the numerator. It's 16 FLQ squared d to the 5th 2g pi squared, just by carrying through that area squared term. And then finally that is h sub f is 8 FLQ squared divided by d to the 5th g pi squared. And so when we rearrange it one more step in terms of d, that's where it came from. It came from just the Darcy-Weisbach equation where we substituted in what we meant by area, and 8FLQ squared h sub f g pi squared, and that's to the 1/5 power. So it's not quite as strange as it first appears to be. Now, when would you use this formula? Basically, you would use this formula when you know how much head loss there's going to be at a system, because you know how highly elevated a tank is, or you know how much pressure is being added by a pump, and then you know already the length of pipe that has to be there, and so the flow rate is going to dictate the diameter of the pipe. Now, what makes it tricky, though, is the F value, because remember from the Colebrook equation, you know, the F value is hard to calculate because it's explicit, but even if we use the Jain equation, which is the explicit equation, even if we use the Jain equation, it's tricky because anytime we change the diameter of the pipe, we're changing the velocity of the pipe inside of the velocity of water inside the pipe. So we have to do this in iterations, and that is what we're going to do with this accurate but a little bit more difficult approach for finding what size of pipe is needed. We're going to work through an example where we look at the diameter needed for a certain flow rate, for a certain known pipe length, and for a head loss that's known in advance. So here's the kind of the workflow that we're going to use in the example. We're going to start off, because we have no other basis, of just guessing some F value within this range. And the range of usual values is 0.08 to 0.038. I'm sorry, 0.008 to 0.038. And you know, we talked earlier about starting with a good guess value. Maybe just picking somewhere in the middle is a good starting point for that. Now, based on the F value, we're going to find out what should the diameter be, because we'll already know the Q, we'll know L, H sub F will be known. F, this friction factor, is really going to be the only thing that so far is uncertain. But then once we have that diameter, that tells us the actual Reynolds number, or we can calculate the Reynolds number, because once we know the diameter of the pipe, then we can calculate the velocity, and with the velocity we can calculate the Reynolds number. And so these steps here are all about having a new and improved F value, and then with an updated F value we put it back into this formula for D, and we keep matching, we keep iterating this process until the F value isn't changing anymore, until your assumed value for F at the beginning of a step is the same as the calculated value for F at the end of a step. All right, so let's do that with this situation. We have an origin where the water is flowing through here and coming to some sort of an outlet, and through the course of that transit it's losing 45 meters of head. We don't know the diameter of pipe that's needed for this 40-meter section, but we do know it's cast iron and it's carrying 300 liters per second. We're going to use Excel for this one. We're going to start with an assumed value of F to calculate the D. Then we're going to, with this calculated D, find out what's the Reynolds number and the relative roughness, and have the Jain equation tell us a new and improved value of F, then go back into this formula and get the new diameter based on our improved guess value for F. Keep repeating until there's convergence, meaning that there's no more change in the F values. All right, so back here to Excel. All right. I'm going to paste the formulas in just so that we've got them handy as we're working. Here's the D formula, and we're going to use the Jain equation rather than Colebrook. All right, so I'm going to put in some givens. Our flow rate from the problem description in terms of cubic meters per second is 0.3, right? Because did it say 300 liters per second? All right. And now we have the K sub S. I'm going to write this one in terms of meters, 0.00026. The length of the pipe section is 40 meters long. G, meters per second squared, 9.81 The H sub F, which is the head loss, and the flow through the pipe is 45. And the kinematic viscosity of water, meters squared per second, is 1 times 10 to the minus 6th. All right. In iteration 1, guess I don't need that to say or. Okay, starting off with iteration 1. We're going to, first of all, assume an F value. And just to show how good this process is, let's start with a bad F value guess. And we know it's probably not way out here in the margins, but we'll start with a bad guess just to see how long it takes for it to converge. Okay, the second step here is to calculate the D based on assumed F. Okay, and I'm going to be using this formula for that. Okay, so D in terms of meters is, I'm going to type in the formula, it is 8 times L, anchoring that, times Q squared, anchoring Q squared, times F, and now divided by H sub F divided by G divided by pi squared. Okay. And now, once I've got, let's see, this was the closing one. Yeah, now I have to take that to the 1/5 power. So that's to the power of 0.2. Okay, so did I get that right? 8L Q squared times F, and then having all these divided bys is the same as if I had a parentheses and then was multiplying them. Divided by H sub F, divided by G, divided by pi squared. All right. So now with that value of F, let's determine the flow conditions. Okay, the Q value is going to be cubic meters per second, and we get the Q, that's already known. From the problem statement, it was the same value as before. But now I also want to know the cross-sectional area for the diameter I just calculated. The cross-sectional area is going to be pi times d squared divided by 4. Okay, so I've got some cross-sectional area. The velocity, in terms of meters per second, is q divided by a. Now let me pause for a moment so that if you're working on things, you can catch up. Any questions so far on like the basic structure of the solution? I mean, having the main idea is what's really important at this point. All right. Now, if we've got all that, we can calculate the Reynolds number. So the Reynolds number is going to be velocity times v times d diameter divided by the kinematic viscosity of water. I'm going to anchor that because I always want it to look in the same spot. I haven't anchored some of the other cell references because what I'm going to do is I'm going to copy this entire block and paste it lower down, and then I'm going to tinker around with the values. So that's why I haven't anchored some of the cell references after that first calculation of D. Okay, so here's the Reynolds number if the diameter was this, which is what the diameter would be if this was the F value. But how good was that guess of the F value? So step 4 is going to calculate a new value of f. So using these flow conditions and assumed d, well, I guess it wasn't assumed, it was calculated, find improved f value. Okay, so we're using the Jain equation here. So I'm going to call this f new using the Jain equation. Now here is the Jain equation. Let's bring it down so it's visible. 1.325 divided by the logarithm of k sub s divided by 3.7 divided by d. Now my units match up. That's why I did the k sub s here in terms of meters, is because I knew that I was going to be calculating d in meters. So I'm just in my mind knowing that the units do match up. Now I have to do plus 5.74 divided by the Reynolds number to the power of 0.9. Okay, and I'm going to remember that squared term. That's the common one that's easy to overlook. But here's our new updated value of f based on what this calculated d and the resulting Reynolds number that comes out of that. And this is expressed right now as scientific. Let me change that to just general. All right, that shows that the first guess of f value was pretty bad. And so we've had a big change in the f, which means the solution is going to be converging quickly. Sometimes in iterations, the convergence is slow, but I think we're going to get the f value to stabilize within just maybe 2 or 3 iterations. This is going to be converging pretty quickly. Okay, so now what we do is we repeat the whole thing. So I'm going to copy all of this, Control C, and then Control V to paste. I'm going to rename this iteration 2. Now, this assumed value of f, instead of having the 0.008 from before, I'm going to just have equals and use my old value, the one that I had calculated in the previous step, as the input. And then the nice thing is, we'll make sure it's looking in the right spots. This guess value of d, it's looking up here at the original data, so it calculated a new diameter needed. So it didn't change the pipe size too much. It went from about 0.14, 0.17. That's going to change the flow conditions. So the flow rate, I should have anchored that flow rate. I didn't. So let me fix that. The flow rate is always going to be the same, 0.3. All right. So the area, want to make sure it's referring to the diameter. It is. The velocity, it's just Q divided by A. The Reynolds number, everything's fine there still. V times D divided by the kinematic viscosity of water. All right. And then we have the improved value of the F. So Jain equation is only changes here is we've got a different D and a different Reynolds number. I didn't what? In the F value? Let's see, where is it looking? K sub s. So that's above the 3.7, this one? Ah, good catch, you're right. All right, so yeah, it's looking in the wrong spot. It's looking at the Reynolds number right now. So let me fix that. Okay, so it was right on the first one, right? But not subsequent ones. I should have anchored that. All right. So here, it's the same equation, but it should be looking at K sub s. All right, so if I paste it again, now it'll be properly anchored. All right, so So how much did the F value change? Our input F value at the beginning of the iteration was 0.023, and normally we only repeat F values to about the 1,000th place. We're getting really picky to the 10,000th place. So it changed a little, not a lot. But let's do it one more iteration just because it's easy at this point. Now that we've got everything anchored correctly, we should be able to select all this data and then Control C, Control V. The hardest part is just changing where it says 2 to 3. Now we're on iteration 3. The input value is already looking at the output of the previous step. We get some new diameter, so the pipe diameter changed a little. The F value changed really a little, and it's probably not going to change at all if we were to do a fourth iteration. So iteration 4. And I know I've been focusing a lot on the F values. I guess I missed a, I should highlight everything here when I copy and paste. All right. Boy. All right, iteration 3. Highlight everything, copy it, paste it. So here's iteration 4. Really what we need to focus on is whether the diameter is changing much from iteration to iteration. And here it's saying 0.17 meters. Here it's saying 0.17 meters, even though there's some slight movement in the F value from the input to the output. Not much, but this is the diameter that we need. So that's an iterative method for solving. There also, I'm just realizing I have a watch on. Now we've still got some time, right? I want to give you back that time I took on the first day. I owe you a few minutes. So we'll let out a little early today, but we're supposed to finish at 4:45, right? All right. It's an awkward thing starting at such an odd time. I don't want to accidentally overlook it. So any questions related to this iterative process? Yes, in the back? Yeah. I mean, but like, what's to check, right? I mean, you got it. Yes, I will upload this, but usually I won't, because you know, usually I'll give you more advance notice that you're going to need your computer, and I mean, we've got the time so that you'll be able to get it right during the class, ordinarily. It depends on how you define easier. Let me show you the easier way. All right, so the easier way to do it is this formula. And, I mean, it's direct. It's a little bit less accurate. You know, what we were just doing, you know, Jain is pretty good, and since it's iterative, that's pretty good. But this is an explicit approach that doesn't require iteration. So you solve for D given this formula. So let's try it out. Solve this formula. And it's really tough to get through it without accidentally punching in the wrong number in the wrong spot. But let's give it a shot. We have, for this one, the explicit equation. Remember, the diameter, the K sub s, is 0.00026 meters. That's a 0. All right. L is 40 meters. Q is 0.3 cubic meters per second. G, of course, 9.81 meters per second squared. H sub f is known to be 45 meters. And then the kinematic viscosity of water is 1 times 10 to the minus 6 meters squared per second. And that's all you need. All right. So let's solve for that. Find what diameter would be recommended by this formula. Okay, so in this case, it turns out to be fairly good. You know, when we did the iterative approach, it was telling us we needed a pipe diameter of about 0.1707. And here it's saying 0.175. So whether it's easier, I suppose we don't have to iterate, but that's an awfully complicated equation to key into the calculator. Then there's not always going to be an explicit backdoor approach like this for all of the iterative problem solving that we have to do in Excel. I mean, today it's sort of, you know, we're getting used to the iteration just because it's going to come up later on. Any questions related to this? Yes? Yeah. Good question. Yeah, so you know, like 5% doesn't matter. It depends on when you're on the border of a pipe diameter threshold. You know, here we've been calculating pipe diameters as though you can order a pipe that is 0.1707 meters in diameter. And you know, they don't make pipes exactly that size. There are sort of steps. You know, there would be 150 millimeter pipe diameter, then you'd have to go to a 200 millimeter pipe diameter. And so if this is saying that you need 0.0175, well, it doesn't really matter because you are going to have to step up to the next larger pipe size anyway. But when it would matter is if you did this shortcut approach and it said, let's say you need 205 millimeter pipe, but you really could have gotten away with one that was smaller, like when it artificially bumps you up to the next pipe size when you maybe didn't need it. So and that's sort of what comes to mind is when that 5% is going to end up having a difference. Okay. That's it for today.